Hello students, welcome to lecture 19. Today we will continue our topic on SVMs. In particular, we will study a soft margin form of support vector machines, which allows some of the points to be misclassified in order to deal with non-linearly separable data. We will see that soft margin SVMs in combination with the kernel function form a powerful model. In the previous lecture, we have seen a different formulation of SVM that uses kernel functions. We introduced the kernel trick, which again uses a kernel function as a shortcut of transforms with inner products. We have introduced commonly used kernel functions, such as polynomial kernel, Gaussian kernel, and linear kernel as a special form of polynomial. Today, the outline is as follows. We will introduce the soft margin SVMs and we'll discuss the motivation and behind the soft margin SVMs. We will then derive the dual form of the soft margin SVMs and we'll discuss the main messages behind SVM, and finally we will stop by model selection examples for soft margin SVMs. Let's start with the cons of hard-margin SVM. When we, for example, transform X to a high-dimensional feature space or an infinite-dimensional one using the Gaussian kernel, for instance, we can easily overfit the data. Okay? The figure here depicts this situation. If we use the Gaussian kernel with a hard-margin SVM and train the SVM model, it insists on finding the two outliers that are misclassified by a linear classifier, which will result in an unnecessarily complicated decision boundary. That should be the sign of overfitting, right? So only for two datas located here, and then here, the Gaussian SVM will try to find this sophisticated decision boundary. For this data, we should probably use a simpler linear hyperplane rather than the complex Gaussian separator, as in this case. Right? There are only 2 points, this one and this one, which make the data linearly not separable. We can simply accept some errors, those two in particular, and using the, for instance, hard-margin SVM, because it cannot solve linearly not separable data, because it is designed for perfect classification of separable data. So one remedy is to consider a softer version of SVM, soft formulation, which tries to get a large margin hyperplane, but which allows small violation of the margins, or even some classification errors. So the main goal today is to derive a formulation of SVM that controls the model's sensitivity to outliers, to small outliers. Recall that the main idea of Pocket PLA, Pocket Perceptron Learning Algorithm, is to minimize the following error function. This is the 0, 1 error function. Also recall that the PLA, Pocket PLA, tries to give up some noisy examples, since the original perceptron is not able to separate data that is not linearly separable. But Pocket PLA again tries to find the best weights, W, and then bias with minimum possible error, okay, which does not require the hypothesis to be perfect. Can we change the hard-margin SVM similar to Pocket PLA so that we can give up some of the noisy examples? Well, This is the original formulation of the hard-margin SVM, which assumes the data to be linearly separable. We can try to combine the objective of the SVM with the following pocket PLA objective function. This will allow us to maximize the margin while allowing some of the examples to be misclassified. For example, here, to maximize the margin, and we allow some of the examples to be misclassified. Note that the minimizing the weight, finding the W and B, will maximize the margin of the hyperplane. This is the first step of our combined objective. The second term can be treated as a noise tolerance as well. This is 0-1 error function. Okay, for the given W, for the hypothesis, make sure if it is making any classification or tolerate any kind of noise. Right? Also tries to minimize the 0-1 error, while we're not requiring all the examples to be perfectly classified. So we have two terms that needs to be minimized: the weight and then misclassification term. The C is a trade-off constant of a large margin, and then the noise tolerance. The C is user-defined. Now, we also need to change the constraints. The first constraint asks all points to be classified correctly. And second constraint is an interesting one. Okay? Which says that for incorrectly classified points, the following should hold true. It should be greater than -infinity, which means the first constraint is violated, right? So if any point is correctly classified, it should be greater than or equal to 1. If not, then higher than -infinity. Now, as you can notice, the new optimization is more complex, since we have another constraint that accounts for incorrectly classified points. So, can we minimize this combination of pocket and then hard-margin SVM optimization? As a first step, we can combine two constraints into one by using the 0-1 error, which is shown here, and using the -infinity. If there is an incorrectly classified mistake, then the 0-1 error will be true. Okay? And we will be penalized by -infinity. So we will have 1 minus negative, means a huge negative number, which again represents that the current example has been misclassified. Also note, if there is no misclassified point, then the 0-1 error will be 0. This is a Boolean function, leaving us this term, right? Y of this term greater than 1, and this will disappear. Well, look, 0-1 error is nonlinear. It's not smooth. And the new optimization here is also not quadratic. Given this formulation, can we derive the dual? Or can we use the kernel function in this combined optimization? Well, another important point is that the constraint cannot distinguish between small error, okay, which is slightly away from the margin, or large error, which is far away from the margin. We can try to do the following changes to form an equivalent problem where we just record the margin violation by the following parameter with linear constraints and penalize the margin violation instead of the error count. We can obtain the common formulation of the linear soft-margin SVM as follows. After introducing the amount of margin violation by the following Xi for each data point n. Okay, we have n data points, and we require that these Xi to be greater than or equal to 0 for all examples, and the following constraint 1 minus Xi. Notice that in this definition of separation, the point is separated if yn w transpose z plus b is greater than 1 and xi is equal to 0. Well, here the xi captures how much a point fails to be separated. If you look at this, okay, large margin demonstration figure, we can see that in terms of margin, the y w transpose z plus b will be equal here, okay, along this margin, in the hard-margin SVM case. Then the data point will be on the boundary of margin. This point, for this point, for this point, for this point, these are support vectors. The following inequality will be equal to 1. So we can think of the xi as the following point, which captures how far into the margin the data point can go inside. The hyperplane is here. This point is still on the correct side. Right? So the margin in this case, it will not be hard anymore. It will be soft because we are allowing the data point to penetrate the margin. Okay, that's why we call it as a soft SVM. So we're allowing this point to penetrate the margin again, only a few points. And we capture these by xi. Right? Note also that if a point satisfies the following inequality with the xi is 0, then the margin will not be violated. And again, the corresponding xi for that point will be 0. Ideally, we would like the total sum of the margin violations, as represented here, to be small. Okay, so with that hope, we modify the hard margin SVM to the soft margin SVM by still allowing margin violations, some of the points like this. However, with the added penalty term, C times xi z, to discourage large violations. We see that the C is a trade-off parameter between large margin and obtaining large margin and margin violation. So for large C, we will see we want less margin violation. For small c, we want large margin. Because our objective function is now consists of the both minimize the first term, also we want to minimize the second term, and c is user defined. We also note that the following new formulation of the soft margin SVM is a quadratic programming with d plus 1 variables, okay, and 2n constraints because of the xi addition. So we can try to remove the dependency on d dimensionality by deriving the soft margin SVM dual formulation. We need to solve this soft margin SVM optimization problem and obtain our weight, optimal weight, and then the bias. We get a large margin by minimizing the first term in the objective function, and also note that we get small violation by minimizing these terms, c. By minimizing the sum of these two terms, we get a compromise between our two goals, and that compromise will favor one or the other of our goals, which is obtaining large margin versus small margin violations, depending again on the user-defined penalty parameter denoted by c. Also note that when c is large, it means we care more about violating the margin, which gets us closer to the hard margin SVM. When C is small, on the other hand, we care less about violating the margin, and by choosing C appropriately, we get a large margin hyperplane with small effective VC dimension and with a small amount of margin violation. So C, the role of the C is very important here, parameter C. We can solve this problem using quadratic programming approach, just as we did in the hard-margin SVM. Well, the soft-margin version, as we can see, is another convex quadratic programming problem. And the corresponding dual optimization form can be derived using the same technique we used in hard-margin SVMs. In other words, using a Lagrangian technique. The Lagrangian function here is denoted by L of B, W, Xi, alpha, and B. The new dual variables that we added in soft-margin SVM are the following: beta and then C. B and W, primal variables, right? We want to derive a Lagrangian dual represented in terms of dual variables, Xi, alpha, and B, right? Oh, alpha and B. So Xi is a primal variable, along with W and B. This is our next step. So, taking partial of Lagrangian with respect to Xi and equating it to 0 gives us the following. Okay? The KKT condition tells us that the optimal solution of these has to be 0 with respect to Xi. That is, alpha and then beta sum to C, right? If we add alpha to beta. We can then replace it as B is equal to C minus alpha without the loss of optimality. If we do so, the Lagrange dual problem simplifies to the following. We substitute the B's. However, we know that Xi can be removed. Again, like how we removed the bias B in the hard-margin dual SVM. Here, look, the inner problem, the minimization problem, is the same as hard-margin SVM. Okay, so if we differentiate with respect to bias and then the weights, we obtain the following. So partial of L with respect to bias, we equate to 0. Without the loss of optimality, we obtain the following, which is the same condition derived in hard-margin SVM. L with respect to W equal to 0 is again same. We represent the weights as a linear combination of Lagrange multipliers in our examples, training examples. Y's are, again, the labels. Remember, the alphas are mostly 0. Only a few of them are non-zero that are coupled with support vectors. We can derive the standard dual as we did in lecture 17 by substitution. I leave it as an exercise for you to go through all the steps as we did in deriving the dual of hard-margin SVMs to get the whole dual for the soft-margin SVMs as follows. Here, this is a dual of soft-margin SVMs. And if we compare the hard-margin SVM here, the only change we note is that the dual problem, in dual problem, each alpha is now upper bounded by C. This is the penalty rate instead of, in the hard margin case, we had infinity, positive infinity. We didn't have any upper bound. That's the only change. And there is, we note that this is another convex and quadratic programming problem. We have n variables and 2n plus 1 constraints, since we have also the following terms. The dual formulation can again be solved by some general or specifically tailored quadratic programming packages. Given data with the corresponding labels, we first compute the Q matrix using the kernel function, and we define the standard form acceptable by the quadratic programming solver by defining A, C, and then P. Second, we run the quadratic programming solver and obtain the alphas as solutions. What about the beta? We can use KKT conditions later again. So the bias we calculate from support vectors. And utilizing the kernel function, okay, once we have the support vectors and their alphas as well as the bias, we can define the following GSVM for soft margin support vector machines as a decision function. For this soft margin SVM, as we can note, we get a similar expression for the final hypothesis in terms of the optimal dual solution, just like that of the hard margin SVMs. Nothing changed in this case. The kernel trick is still applicable in soft margin SVM case as well, as long as we can calculate the B bias efficiently, which is the question here. How can we calculate the bias? Solving for optimal bias B from using the optimal alphas in soft margin SVM is a bit more difficult or complicated than the hard margin case. Well, in hard margin case, we used KKT conditions that state the following. Either alpha should be 0 or the inner term, right? We said that for when alpha is non-zero, we can solve for the bias and find the solution of the bias as follows, represented in terms of weights and examples for non-zero alphas. Likewise, or similarly, we can use the same KKT conditions to solve for bias, right? Which will be equal to the following. For non-zero alphas, B is equal to YS, YSC minus WTNC. And we also have, let's say, for non-zero alphas, and then we have upper bound to alpha, which is C. Okay? If alpha is upper bounded by C, which means Xi is 0. And we recover the following. So these two inequalities can give a range for these two for optimal bias. So if there is a support vector that range between 0 and then C, we can see that the inequalities can be combined to an inequality, and then we can solve for bias. For separable data in the transformed space, there exists some C, the parameter, such that, okay, so C in the soft margin produces exactly the same solution as the hard margin. Okay, as a result, we can relate hard margin SVM as a special case of soft margin 1. Here, for example, let's take a closer look at this, the role of the parameter C in the soft margin SVM formulation. If C is large, as shown here, it means that we do want all violations or all the error to be as small as possible, with the possible trade-off being a smaller margin, which leads to highly complex boundary. If C is small, That means we can tolerate some amount of errors or noise while possibly getting a less complicated hypothesis with large margin. When C is in the, let's say, in between to low to high is equal to 10, we see a bit more complicated boundary, right? So here we are giving up some of the points. While when the C is high, it will try to correct all the mistakes without violation using, let's say, the Gaussian kernel in this case. Well, when C is equal to infinity, we recover hard-margin SVM. So note that depending on the choice of the C, we can overfit or underfit, right? There is always the risk of overfitting. So we need to be careful in selecting C plus the kernel parameter. In Gaussian, we have gamma, the width of the Gaussian function. We can try to interpret the meaning of alpha, the solution, to soft margin case physically, right? First, non-support vectors will have alpha 0. Those points far away from the boundary, and Xi will be 0. We will have support vectors within this range, 0 to C, with Xi is equal to 0. We call them as a free support vectors, which are guaranteed to be on the boundary of fat hyperplane. Therefore, they are also called as margin support vectors. Okay, the support vectors with alpha equal to C, on the other hand, are called bounded support vectors. We can also call them as non-margin support vectors, represented by those triangles. As you can see, they can be on the fat boundary, slightly violating the boundary, but still on the correctly side of the hyperplane, correctly predicted classifier, or seriously violating the boundary and erroneous predicted. When the regularization parameter C and then the kernel function are chosen properly, let's say the Gaussian kernel with the proper gamma, the soft margin SVM is often observed to enjoy a low out-of-sample error. These properties of SVM make them to be one of the most classification models and often the first choice in learning from data, especially when you have limited amount of training data. It's a robust linear model with advanced nonlinear transform capability when used with a kernel. Okay? However, choosing the parameter C and then the kernel parameter gamma in Gaussian kernel, right? Polynomial kernel has two parameters, needs to be defined usually within a model selection step. Now, the question, how can we select the optimal parameters now or in the soft margin SVM? Let's say C and gamma, we have two parameters. One way to select the optimal C and gamma for Gaussian soft margin SVM is to use cross-validation. For example, we can try different combination of gamma and then C and observe the cross-validation error measures, right? And finding these optimal two is actually a combinatorial problem, which is not easy anymore. Nonetheless, we can still use techniques called grid search in combination with a cross-validation, defining a few grid values of C and gamma. And we can use cross-validation error as a criteria for selecting the soft margin SVMs with good C and gamma. For instance, in this figure, we can see different combinations of gamma and C leads to different decision boundaries. And then the cross-validation errors, as shown here numerically, right? So we can select these hypotheses, for example, this more like a linear SVM, using the following cross-validation error on a grid of, again, C and gamma. So one pair of C trade-off, margin trade-off parameter and kernel parameter will eventually give us a model soft SVM with small cross-validation error. This is what is used in practice. So cross-validation to identify the optimal C and gamma. So, in summary, the soft margin SVMs can deliver a large margin hyperplane, and in doing so, it can control the effective model complexity. Also, note that the soft margin SVMs can deal with high or infinite dimensional transforms employing the kernel trick. They can also express a final hypothesis G using only a few support vectors with their corresponding Lagrange multipliers, which are non-zero, and the kernel. Another property of the support vector machines, soft margin SVMs, that they can control the sensitivity to outliers and rigorize the solution through setting the margin trade-off parameter C.